Round to even is one of several rounding modes available on the x86. It's used most often to round the mantissa of a floating point number, and for that purpose it's the default. In fact, it's rather difficult to get any of the other rounding modes without dropping into assembly language. In this video, we'll explain how round to even works and why it's a reasonable rounding strategy. At the machine level, we're dealing with binary numbers, but we'll illustrate the concept initially with decimal because it's more familiar. Consider the three cases shown here: 2 1/3, 2 2/3, and 2 3/4. Now let's add the decimal expansions of these numbers. By the way, even when the decimal expansion terminates, as with 2 3/4, you can always pad with zeros into an infinite sequence of digits. Now suppose that we need to store an approximation of these values to the 10th position, that is, such that there's a single digit to the right of the decimal point. Let's call that the rounding point for this problem. We could do this approximation in several different ways. For example, we could always round up to an appropriate value that is, effectively, the least upper bound on our number in the prescribed format. Or we could always round down. This would yield the greatest lower bound on the approximation in the right format. But for large data sets, either of these choices would tend to bias the values. If we consistently rounded up, on average, we'd be adding a 20th to each value. And if we consistently rounded down, we'd be subtracting a 20th on average from each value. This problem can be partially alleviated by using round to nearest mode. This means that if the value to be rounded is closer to the round up value, we round in that direction. If closer to the round down value, choose that. This reduces the systematic bias substantially. However, it leaves ambiguous the case where the value to be rounded is exactly halfway between the results of rounding up and rounding down. For a decimal fraction, this occurs if 5 is the single digit to the right of the rounding point, or in padded version, if the digits to the right of the rounding point are 5 followed by an infinite sequence of zeros. We could choose always to round up or always to round down in this one case, in the hope that it's relatively rare. But in a very large data set, this still might bias the result. The round to even rounding mode solves this problem as follows. Use round to nearest unless the value to be rounded is exactly halfway between the round up and round down values. In that case, choose whichever of the round up or round down values has an even digit to the left of the rounding point. The even digits are 0, 2, 4, 6, and 8. It's guaranteed that exactly one of the two choices will have an even digit, so the choice is unambiguous. To see how this works, let's consider rounding 2.75 to the 10th position, that is, leaving one digit to the right of the decimal point. This is a case for round to even. Note that 2 3/4 lies halfway between 2 7/10, or 2.7, and 2 4/5, or 2.8. The round to even rule says to pick the result that has an even digit to the left of the rounding point. So in this case, we pick 2.8 over 2.7, since 8 is even and 7 is not. Let's look at another example. Suppose we want to round 2.995 to the 100th place, that is, leaving two digits after the decimal point. Note that 2.995 is exactly halfway between the round up value of 3.00 and the round down value of 2.99. So we choose to round up to 3.00, since that leaves an even digit, 0, to the left of the rounding point. The assumption of round to even is that for most data sets, only a small percentage of cases will fall exactly between the round up and round down values. Of these, approximately half will be rounded up and half rounded down by the round to even rule. This will generally avoid rounding introducing any systematic bias, even for very large data sets. Suppose that our numbers were negative instead of positive. For example, consider rounding minus 2.995 to the 100th place. Notice that this is exactly halfway between minus 3.00 and minus 2.99. As usual, we choose the rounded value with an even digit at the rounding point, namely minus 3.00. In this case, we're rounding down rather than rounding up as we did with the positives of these numbers, but the calculation is otherwise exactly the same. By the way, you can always compute the rounded down result by simply dropping the 5 following the rounding point. Compute the rounded up result by dropping the 5 and then adding 1 just to the left of the rounding point. That's equivalent to adding 1/20th if you're rounding to the tenths position, adding 1/200th if rounding to the hundredths position, and so on. Finally, let's consider how we apply the round to even rule to binary numbers. A binary fraction is exactly halfway between the round up and round down values when there's a single 1 to the right of the rounding point, or in the padded version, 1 followed by an infinite sequence of zeros. For example, suppose we want to round 2 3/4 to the halves position. That is, we want a single bit to the right of the binary point. In binary, it's shown here. To compute the round down result, drop the 1 following the rounding point. To compute the round up result, drop the 1 following the rounding point and then add 1 at the rounding point. When we do that, we see that our fraction falls halfway between the values shown here. Now the choice is easy. Choose the value with an even bit at the rounding point. In binary, 0 is the only even bit, so we choose 11.0. Let's consider a few more examples. In all the following, we'll be rounding a binary fraction at the 8ths place, that is, leaving 3 bits to the right of the binary point. Consider the following. In this case, what follows the rounding point is larger than 1 followed by an infinite series of zeros, so we'll round up to this. Consider a second case. Here, what follows the rounding point is smaller than 1 followed by an infinite series of zeros, so we round down to this. Finally, consider a third case. Here, what follows the rounding point is exactly equal to 1 followed by an infinite series of zeros, so we must round to even. The round up and round down values are shown here. We choose to round up to 11.000.